Deformable 3D Gaussians for high-fidelity monocular dynamic scene reconstruction. Given a set of posed images of a monocular dynamic scene, our goal is to reconstruct high-fidelity scenes. However, existing state-of-the-art methods primarily face three issues. First, current SOTA methods based on NeRF's implicit representation have a significant time overhead for raycasting, limiting their potential for real-time and high-resolution rendering. Second, although some hybrid methods have accelerated training and rendering by introducing structures like grids or planes, there is still a considerable gap in real-time rendering. Additionally, constrained by the low-rank tensor assumption, dynamic scenes, compared to static ones, have a higher rank that restricts their high-fidelity rendering. Third, previous methods all rely on backward flow to model deformation, which is also a potential factor limiting rendering quality. To illustrate what backward flow is, we take NeRF as an example. NeRF first performs raycasting sampling in observation space to render an image. To obtain the attributes of the sampled points in observation space at a specific time t, NeRF maps the sampling points to the canonical space through a deformation field, and then obtains the corresponding pixel color in observation space through NeRF's implicit representation and volume rendering. This backward flow leads to unclean mappings. To solve the above three problems, we proposed deformable 3D Gaussians, which learns 3D Gaussians in canonical space and models deformation through a purely MLP. Unlike previous methods, we map 3D Gaussians from canonical to deformed space using forward flow. It can produce accurate mapping to render 3D Gaussians in deformed space. Thanks to the highly efficient and high-quality point-based rendering of 3D Gaussians, we achieved both high-fidelity details and real-time rendering speed. We show the results of our approach in monocular dynamic scenes. First is the Blender synthetic dataset. It is evident from the results that the 3D Gaussian-based forward flow strategy significantly outperforms the previous NeRF-based backward flow strategy. Our method can also be applied to real-world datasets. Experimental results show that in scenes where the camera pose is relatively accurate, our method can achieve the best rendering quality and speed. Compared to Hyper-NeRF, NeRF DS has more accurate camera poses. Therefore, we use this dataset for quantitative evaluation of the applicability of our method in real-world datasets. We also show the superiority of our method in the task of novel view synthesis. In our experiments, we found that camera pose estimation in real-world scenes always has deviations. We proposed annealing smooth training, which introduces an annealing smoothing term for time t during the training process. This not only improves the smoothness of the time interpolation task but also enhances the quality of rendering. We also validated the superiority of our method through quantitative experiments. On the D-NeRF dataset, we increased the overall PSNR to nearly 40 at full resolution. On the NeRF DS dataset, although our method did not achieve the best results in some scenes, it obtained the best overall rendering quality. It's worth noting that annealing smooth training achieved better results in almost every scene. Thank you for watching.